For the binary decision making shown in this figure, there are two ways error can occur. An error E will occur when S1T is sent and channel noise results in the receiver output signal Z being less than the threshold gamma 0. The probability of such occurrence can be written as P E given S1 equal to minus infinity to gamma 0 Pz given S1 dz. So this section is that probability, the shaded region. Similarly, an error occurs when S2 is sent and the channel noise results in Zt being greater than gamma 0. So the probability of such occurrence can be written as Pe given S2 equal to gamma 0 to infinity Pz given S2 dz. Now, the probability of an error is the sum of the probabilities of all the ways that an error can occur. For binary case, this can express the probability of bit error as Pb is the summation of these two that is equal to Si. Pe given Si, Psi. This Psi is the a priori probability of ith symbol. So expanding this, you can write Pe given S1 PS1 plus Pe given S2 PS2. If we call this as hypothesis H1, this one as hypothesis H2, then this equation can be written as PH2 given S1 PS1 plus PH1 given S2 PS2. That is, given that signal S1 was transmitted and error results in hypothesis H2 is chosen, or given that signal S2 was transmitted and error results in hypothesis H1 is chosen. So for the case where the a priori probabilities are equal, is the simplest situation. PS1 equal to PS2. Two probabilities are equal, that is equal to half. Same probability in binary system. So PB can be written as PH2, half of H2S1 plus half of H1 given S2. And because the symmetry of the probability density functions, we can write this is nothing but H2 given S1 equal to P H1 given S2. the probability of a bit error PB is numerically equal to the area under the tail of their the that means tail means this portion, maybe for this case this one, for this symbol, or for this symbol, this tail. So any one likelihood we can take. That means when it falls in the incorrect side of the threshold. So we can compute PB by integrating say PZ1 between the limits minus infinity to gamma 0, or by integrating PZS2, this one, from gamma 0 to positive infinity. So we can write PB equal to A1 plus A2 by 2 half. Well, from the discussion with maximum likelihood decision rule, if this one is the maximum probable value A1 for symbol S1, and A2 is the maximum probable value for symbol S2, and for a priori probabilities when they are equal in binary system, then the threshold should be chosen as A1 plus A2 by 2, that we have already seen from our discussion with the maximum likelihood decision rule. So we can write P Z given S2 dz now we will assume that this Pz S1 given S1 or Pz given S2, that means the likelihood with their Gaussian equivalent form. So if we consider this, then given S1 is equal to sigma 0 root over 2 pi exponential minus half z minus A1 by sigma 0 square. Also, in identical fashion, Pz given S2 equal to 1 by sigma 0 root over 2 pi exponential minus half z minus A2 divided by sigma 0 square. Sigma 0 square is the noise variance. So if we use these notations for Gaussian PDF, we can write PB equal to gamma 0 equal to A1 plus A2 by 2 to infinity 1 by sigma 0 root over 2 pi exponential minus half z minus A1 by sigma 0 square dz. Now we will consider, say u is a parameter z1 minus A2 by sigma 0. So sigma 0 du equal to dz. So if we replace this if we make this running variable as u, we can write PB error probability equal to u equal to A1 minus A2 by 2 to u equal to infinity 1 by 2 pi exponential minus u square by 2 du. and this is a standard form of Q function with argument a1 minus a2 by twice sigma 0. This Q function was or complementary error function Qx that approximately be written in this way. This one will be root over x to infinity exp minus d square by 2 du. So error probability takes this form of complementary error function. With this result, we will now try to optimize error performance. So to optimize this error PB, we need to select the optimum receiving filter and the optimum decision threshold. To minimize this PB, it is necessary to choose the filter. Obviously the filter is the match filter that maximizes the argument of that Qx that we have already derived just now. Thus, we need to determine the linear filter that maximizes a1 minus a2 by twice sigma 0, the argument of the Q function, or equivalently that maximizes a1 minus a2 whole square sigma 0 square, where a1 minus a2 is the difference of the desired signal components at the filter output at time t equal to capital T, and the square of this difference signal is the instantaneous power of the difference signal, and this T is the sampling instant. A matched filter maximizes the output signal to noise ratio for a given known signal. Here we view the optimum filter as one that maximizes the difference between two possible signal outputs. So optimum filter means that maximizes the difference between two possible signal outputs. A matched filter achieves a maximum possible output SNR equal to 2E by N0, where E is the energy of the input signal. Consider that the filter is matched to the input difference signal, and the difference signal means the difference between S1 and S2. So this particular matched filter is matched to the input difference signal. So we can write an output SNR at time t equal to capital T. Output SNR at time capital T equal to a1 minus a2 square by sigma 0 square, that is equal to 2 ED by N0. where n0 by 2 is the PSD of noise, assuming it is a white noise at the filter input, and ED is the energy of the difference signal, that is S1t minus S2t whole square dt. This is the energy of the difference signal. If you observe this equation, Sn t at equal to 2 Ed by n0, it does not represent the SNR for any single transmission S1 or S2. This SNR yields a metric of signal difference for the filter output. By maximizing the output SNR, like here this one, the masked filter provides the maximum distance, normalized by noise obviously, between the two candidate outputs, signal A1 and signal A2. So the equation of PB, expression of PB that we got, A1 minus A2 by twice sigma 0 from the error performance, and if we consider this one, and if we combine them, we can write PB equal to Q ED by twice N0. So for masked filter, this equation is an important interim result in terms of the energy of the difference signal at the filter's input. From this equation, a more general relationship in terms of received bit energy can be developed. And to do so, we start by defining a time cross correlation coefficient rho as a measure of similarity between two signals S1 and S2. So we can define this cross correlation coefficient rho equal to 1 by EB 0 to t S1t S2t dt, and also we can define rho as, say, cos theta, where the range of rho is -1 to +1. So this definition of rho is a classical way of expressing correlation. When S1t and S2t are viewed as signal vectors, like S1 vector and S2 vector, then this rho is conveniently expressed by this expression. Where the angle between vector S1 and vector S2 is this theta. So for small angular separation, the vectors are quite similar to each other, and for large angular separation, they are quite dissimilar. And from this equation, we can see that the cosine of this angle between these two signals is the cross correlation coefficient. Now let us again start with this equation. We expand that equation, and we want to write this ED, expression of ED, in terms of this correlation coefficient, cross correlation coefficient. So what we do, we expand this equation for expression for ED, 0 to t s1 square t dt plus s2 square t dt plus minus 2 0 to t s1 t s2 t dt. So this is if we see this expression, that this term and this term, they are nothing but the bit energy, and we have already seen that bit energy is written as EB here. EB is the bit energy. So these two terms are the bit energy EB. That means EB equal to 0 to t s1 square t dt. Similarly 0 to t s2 square t dt. So if we replace this in this original equation, we can write ED equal to EB plus EB minus 2 rho EB. That means twice EB into 1 minus rho. So once we get ED from this equation, we can write the expression of PB in terms of rho. PB equal to Q of root over of EB into 1 minus rho divided by N0. Now we will consider two cases. In the first case, where rho equal to say minus 1, corresponding to S1 and S2 being anti-correlated over a symbol time. In other words, the angle between the signal vector is 180 degree. In such a case, where the vectors are mirror images, we call the signals are antipodal. So if we try to draw the signal space, this is 0, this one is EB, this one is square root of, both of them are the equal. This is S1, this is S2. Here ED equal to 4 EB. Example is bipolar signaling. So this is one example where rho equal to minus 1 and corresponding PB, if we put rho equal to minus 1 right here, corresponding PB will be equal to Q of root over twice EB by N0. Now if we consider another case where rho equal to 0, corresponding to 0 correlation between S1 and S2. So if we represent S1, S2, S1t and S2t in terms of vectors, then we can say for this case the angle between S1 and S2 vector is 90 degree. That means is something like this. Say S1 and S2. These are two vectors. Psi1 are the basis and Psi2 is another basis signal, and the distance between them is root over of 2EB. Hypotenuse is root over of 2EB. So ED will be equal to ED will be equal to 2EB in this case. And if we put rho equal to 0 in the general expression of PB, we can get PB equal to Q of root over EB by N0. So if we plot these two, it will be something like this. So difference between them, this is EB by N0 in dB, and this is PB. This one is for antipodal, and this is for orthogonal. Sorry, this one is for orthogonal. And this outer curve is the orthogonal. And if you calculate, you will see the gap is root over of 2 is there, so it is almost 3 dB gap. That means the orthogonal signal requires 3 dB more signal to noise ratio compared to the antipodal. So antipodal signal is comparatively better in terms of this PB, as far PB is concerned. Let us take one numerical problem, like for a matched filter. Say we have two symbols, S1T and S2T. S1T is given by this figure. T is in microsecond, and this one is in millivolt. S2T we have a opposite polarity. So these are S1 and S2. We are using matched filter reception technique. Assuming S1 and S2 are equiprobable, that means a priori probabilities are same. Now we have to determine the bit error probability. That means we have to, the question is to determine bit error probability for this matched filter. Assuming that PSD of noise is given by 10 to the power minus 12 watt per hertz. So in this case, first of all, we have to determine the bit energy. So bit energy, mind it is microsecond, this one is millivolt. So can be evaluated in this way. We have to take the energy here, here and here. Then 2 into 10 to the power minus 3 volt to 10 to the power minus 6 second plus 10 to the power minus 3 volt square plus into 10 to the power minus 6 second. So we have determined the energy for 3 different regions, and it will be 6 into 10 to the power minus 12 joule. So PV, that we have already determined the expression for PV, that will be for antipodal signal it is Q of root over 12, that means Q of 3.46, and from the table we can determine the expression value of this Q for 3.46 is 3 into 10 to the power minus 4. So this is the answer. This is the bit error probability for this particular system.